we were talking about this example of, if we wanted to compute all the prefix sums or partial sums, we see those things sequentially. We don't have access to the full data set. We can't sample uniformly from it or operate on it. If we do it naively, if we just compute this prefix sum one after the other in the DP way, we would end up paying the price in terms of how much total error we incur, and we said that that error grows linearly with respect to the number of queries that we do, and the epsilon itself also grows like root n, which is the number of times we access. Whereas if we do it in a clever way on a tree, we could actually get epsilon that only grows logarithmically and a noise that only grows logarithmically. We can improve both privacy and the noise of how we compute these things. And the trick is to use this tree and those other advanced ways that I'm not going to get into, but I can give you some reference to it a bit. All right, so let's see how it actually can be used inside of machine learning pipeline, especially the cross-device federated learning pipeline. So this is the slide that compares these two things side by side. And this is still at a very high level. So on the left-hand side, this is DP federated aperture, the thing we talked about in the prior lecture. So we kind of compute the model updates or gradient updates, and we deepify them via the Gaussian mechanism. And we treat those things as separate entities. So we apply the Gaussian mechanism independently every time we do a training run. And so like, the first time we get some sort of an estimate of the first training round gradient, that's G1. And second time we get, again, some sort of a DP estimate of the second round estimate of the gradient G2. But the point here is that we're applying independent noise. And if we want to get formal, strong privacy guarantees, we have to rely very heavily on amplification via sample. Whereas on the right-hand side, this is the new paradigm. Notice what's going to happen. We're not going to compute these things independently and add independent Gaussian noise. We're going to treat it as some sort of a streaming problem. We'll see why in a bit, how we can treat this as a streaming problem. And we're going to add correlated noise. If you notice here, what's going to happen when we start computing these partial sums, the noise is going to get correlated. When we grab different nodes and add them to get those DP estimates of the partial sums, it's really, we're going to try to reuse some of these noise estimates. So let's see why and how we can do that. So it turns out that if you take the if you take any stochastic gradient descent or mini-batch stochastic gradient descent, and if you unroll the algorithm, you'll notice the following. The model update at time step t plus 1 is the model update at time step t minus the learning rate times the gradient that we see at time t, right? In this case, I'm assuming it's like a stochastic gradient descent, so I'm getting only one update, but it can be a mini batch. So this g of t can be an average of gradients at that time. You don't have to think of it as essentially only one single gradient, gt. Now, if you take this and you unroll it, just do loop unrolling. So take gt, take theta t, open it up, write it as theta t minus 1, then take theta t minus 1, write it as theta t minus 2, so on and so forth. Keep on doing it. What you will notice is that theta t plus 1, the model at theta t plus 1 is the initial model, theta 0, which say is a random initialized model, minus the learning rate times, and this is where it all kicks in. There's the prefix sum of the gradients from 0 to time step t. This is the most important thing because this is the connection between this problem, this toy problem, and ML. So in ML, what we're doing is every time we update our model, we're computing a prefix sum, and we're using that prefix sum of gradients in order to update the model. So theta at t+2 is going to be theta 0 minus learning rate times the prefix sum all the way till t+1. Simply, you just take the simple SGD update equation and you unroll it. You just keep on unrolling it to get to the kind of bottom of it. So notice all we need here is this prefix sum. And so we could actually ask ourselves, can we do it in a way that leverages these tricks that we just talked about? So a way that deepifies prefix sums. And it turns out there's a very long literature on this in the DP community that's studied under the rubric of continual learning or deepifying prefix sums. There's hierarchical mechanisms, of which this is one. This is a special case. This binary mechanism is a special case of hierarchical mechanisms. Some people use trees with different degrees, and sometimes there's a gain to be had there. And there's also like matrix mechanisms. I'm not going to go into those. They're a little more advanced, but they have more or less the same properties that this one has. And so all these tricks and techniques can be brought in order to solve this problem. We now view it as instead of independent rounds, we view it as a continual learning problem. So the way we actually, solve this, we call this algorithm DP-FDRL. FDRL stands for follow the regularized leader. The name comes from optimization. It has nothing to do with DP. So you should not care as much about why is it called FDRL, what's the meaning of FDRL. It has no meaning in this context. But it essentially uses this tree mechanism. So you can see here how we're giving this tree the per batch gradients on the leaf nodes, and we're computing the prefix sum of these gradients as we go on the fly. And we do it with DP. And when you put this whole thing together, by the way, this was for binary vectors. You could do it for dimensional vectors. Those are the gradients. You would still need to clip to bound their sensitivity similar to what we talked about. But the same thing. It's the Gaussian, multidimensional Gaussian mechanism. Clipped norms, so sensitivity is bounded. And instead of having only one single gradient, you can have k gradients coming from k users. Everything works out. You should trust me on this one. We can generalize this in many different ways, the dimensions and number of users per one, etc. But when you put it all together, the interesting thing is you can see on this plot is that for a lot of epsilons, this approach actually is pretty competitive with the amplified version of DP FedUp or DP-SGD. You will see the accuracy of this blue curve meets or exceeds the accuracy of the dashed yellow curve. And that's the one with amplification, especially for epsilons greater than maybe around 2 or something like that. Now, for very small epsilons, this method is not as competitive as the one that we get from amplification via sampling, but it's still much, much better than not getting anything. So it still outperforms significantly the unamplified version of DP. So it works very beautifully. And we have variations on it and improvements, and right now we have methods that just do so much better. So this is how we use it in practice with federated learning. We still clip on device. We clip the bound user contribution, so to make sure that the sensitivity is bounded. We have a report goal with a certain number of devices. We ensure that no device can participate more than once every 24 hours. So if we end up training for, let's say, 5 days or 10 days, a device cannot show up more than 5 times during training. We need to bound the number of participations any device can make. That's, again, you need to do some sort of composition of the devices. And then on the server, notice the difference between DP FedUp and this approach. Now we have this tree mechanism. We have this exact tree data structure where we run this stateful DP mechanism to compute those prefix sums with DP. All right, so it fits the federated averaging model very, very good. We could use it at scale. In fact, that is the thing we used in production. 2 years ago, almost, we trained the first LSTM model. Was a small model, especially by today's standards, 1.3 million parameters. It's a recursive neural network. We trained over 6 days. We ensured that no device can participate more than once per day, so per 24 hours. So over the course of 6 days, no device can participate more than 6 times. We trained over 2,000 rounds. That's a very small number of rounds. We had 6,500 devices per round. And the model quality was actually better than whatever we had before this one. So not only we were able to train with DP, we were actually also in the process able to improve the model quality, just because of the architecture that we used at the time and the number of trainings. This was the first time, up to our knowledge, at the time that anybody had trained a model in production at scale with provable formal DP, and I'll tell you what the DP guarantee is. It was literally, up to our knowledge, the first time anybody had done, and now with formal epsilons and proper DP at scale. And we had a blog post still up there if you want to check it out. But since then, we actually improved our offering a lot. So the epsilon that we were able to achieve for this specific model is 8.9. The delta is 10 to the negative 10, so very small, as we said in the first part of this lecture. And we were able to give another guarantee, which is zero concentrated DP, which is a notion that's closely related to differential pricing. These two are just slightly different ways of bounding the distances between the query outputs. And the unit of privacy here is device level. So with respect to zeroing out the contributions of any device, the code is open source, so you can go and inspect it, and you can double check our implementation, and you can verify that we're indeed bounding user contribution properly, we're adding the right noise at the right place. So everything is open sourceable. And the trust model is such that you needed to trust that the server is indeed adding the noise. So you don't have a mechanism for you to verify that the server did add the noise. And so that's essentially a potential weakness of this approach. You need to trust that Google is actually doing what it advertises to be doing. And we'll see in the next part of this talk how we can relax those trust assumptions. So this is our kind of DP fact sheet, which we like to give with this release. Since then, yes?
You had on the previous slide that for well-behaved clients. What does it mean to you?
That's a very good point. So what is a well-behaved client? We said that we needed to bound user contribution and we needed to bound participation. So no device can participate more than once every 24 hours. So if you jailbreak your device and you tamper with the code and you start participating every round, so you provide many contributions, this DP guarantee will not hold with respect. Because with respect to you, we would have to do more compositions, right? You're giving us more updates, more than one update per day. You're giving us 10 updates or 100 updates or whatever it is. So you're not a well-behaved device because you've tampered with your phone. But for all the devices that are actually following the code that we ship and run, then for those devices, this DP guarantee.
But this is like I'm tampering with my own privacy.
Yeah, which I don't know why you would do it, but I mean, in this case, maybe you would just want to attack the training system, and you would want to inject some malicious updates and try to break the model or steal the model or something like that. But we need to be very upfront about what the guarantee is and scope, and with respect to who it holds. So that's why we're giving all that information. Other questions about this release? So this release was a little over a year ago. Yeah.
Another question about so parameters. So how can I think about it? It's also 8.9. What does it mean for like? Is it that to like the best attack possible means that it has like this kind of length or?
Yeah. So I'll talk about attacks towards the end of this lecture. For now, all I want you to know is that this is the DP guarantee we can give, and this epsilon is actually, as you mentioned, a little weak. It's not in the perfect range that we would love to be, like epsilon equals 1 or something like that. As close to 1 as possible, it's actually 9. Since then, we've strengthened it. I'll show you in a bit. we were able to achieve much smaller epsilons for many models. But yes, we are not today at a point where we can train these models, especially the larger models, with very small epsilons. And that's why we need to complement DP with some auditing techniques, the tags, and I'll talk about it.
If I understand correctly, this approach requires to like store all of the gradients from the devices taking part in the round on the server. Is it a problem?
You don't need to store individual gradients. You need to store aggregated gradients, and you do not need all the aggregated gradients, but all of that. I didn't go into the details of how we can implement this tree mechanism very efficiently, but it turns out you only need to keep at any point in time at most log n nodes. You can throw away a lot of things as you move on. So as you go from left to right, you don't need to keep all the leaf nodes and their parent nodes and the parents of the parents. You only need to keep at most log n nodes. In fact, there's a strategy to even improve upon that. And again, those are aggregated gradients, aggregated per round gradients, not individual gradients from users. So yeah, you need to keep some state, and that state is in the form of some raw aggregated gradients, unnoised gradients, you're right, but it's not as bad as it seems.
Okay, yeah, great, thanks.
Cool. Again, this is all central DP. This is all we're trusting the server. The server is not the adversary that we're trying to protect against. It's the data engineer that has requested the model, or when we release the model, we publish it and push it at scale. That's where the adversary is. Again, this is quite important. All right, so since then, Google Keyboard, the app Gboard, went all in on DP. This was the major milestone because Google Keyboard has something like 20 machine learning models, not just one or two. There's literally an ML model for every single thing in that little app. And they decided they wanted to train all their models with federated learning in DP. So you can see here, there's the next word prediction, there's the smart compose, there's the on-the-fly rescoring models that do all sorts of similar but slightly different things. There's the search button as well, and the voice thing in it, all kinds and all styles of models. And they committed that all future Gboard language models, whether LSTMs, transformers, as they get bigger, everything will actually be trained with DP prior to being launched. So this is a major feat. You can read more about it. I have the paper at the bottom of this slide discussing the Gboard launch. But what I wanted to show you on the slide is that it took a lot of effort for us to actually train all these models. As you can imagine, Gboard has users with very different preferences and languages. So there's basically German and French and Italian and Spanish and English and all those languages. And the populations across these languages vary. Some countries and languages have less users compared to others. There's literally certain languages with a few 100,000 speakers or users, and there's languages with tens of millions of users, maybe in hundreds of millions. You can imagine that satisfying DP for languages where there's very many speakers is going to be much easier than for languages where there's a lot less speakers. We talked a lot about the data set size, right? So we have to do a lot of playing with how much compute, the batch size, and how much noise we can tolerate. And that's why if you look at the slide, there's a column here that says ZCDP. There's the privacy kind of columns. And under the privacy column, there's a ZCDP column. That's the privacy guarantee. And you'll see that some of them have a ZCDP. Again, ZCDP is a version of DP. It's not exactly DP. It's a very closely related notion of DP. We can convert back and forth between these two. Okay? And so you can see that some of them are 0.48. That's actually pretty strong. That's the epsilon that's somewhat close to 1. And some of them are weaker. Some of them you go up to 1.8 and something like that. So we cannot give the exact same DP guarantee for all these models, especially for next word prediction models here, but we can give a finite epsilon a reasonable epsilon for all the models. We're committed to strengthening these guarantees, but this itself is a major feat. Just the fact that we can train every single Gboard model with DP is a big leap forward. You can see on the slide, how many training rounds we did for each one of them. You can see a bunch of information about the model itself, so on and so forth. All right, so there's a long line of research that we have been conducting, especially my teammates at Google, that improve on this simple binary tree aggregation kind of protocol. So there's a line of work that's now known under the rubric of matrix factorization DP mechanisms. These are two papers. One appeared in NeurIPS of last year, and one appeared in ICML of this year, just last week. I invite you to check out these papers. They're way more advanced in the way these mechanisms operate. So I'm not going to go into their details. It's not that interesting, especially unless you just want to learn the mathematics of them. But there's room for improvement. But the good news is that each and every one of you here could be picking up one of these papers and trying to actually improve the privacy accuracy trade-offs. When we switched from the binary mechanism class of DP queries to matrix factorization, we saw a nice boost in accuracy, and there's still room for improvement. So we're actually, by the day, improving the privacy accuracy trade-offs. So that is going to help us in strengthening those epsilons and getting stronger variances. And this is actually the most important slide of this talk, which is oftentimes a lot of people come to us and say, will DP work for my problem, for my model, for my use case? And in the past, we used to say yes or no. If they have very little users, or if they had some difficult computation, we would tell them we don't think DP is the right thing for you. It's going to hurt your accuracy and your utility quite a lot. And nowadays, we stop giving that binary yes or no question because we don't believe in it anymore. We think that it's a complex trade-off between how much computation you're willing to throw at the problem and the data set size. So the more users you have, the better these trade-offs get. So the more interesting question to ask here is how big of a population and how many clients per round do I need to achieve good privacy accuracy trade-offs? So those are the types of questions that we always encourage our customers to think about. Rather than, will DP work, yes or no? It's like we try to think, do we have enough compute? Can we form a large enough batch? And can we actually get more clients? Can we onboard more clients or reach more clients? And it's essentially a trade-off. It's not just a two-way trade-off, it's a four-way trade-off between accuracy, privacy, computation, and data set size. And that's the thing that we need to think a lot about, how to improve the Pareto frontier of this trade-off. And those new mechanisms allow us to actually continuously improve the trade-off. Sure. All right, so this is something that I think is very cool, which is, so up to now, everything we saw requires trusting the server. The server has to add the points, and we have to trust that the server is adding the right amount of the right points. So a very interesting line of research that we and others in the community have been looking at is how to actually relax the trust and remove as much trust as possible in the server. And that can only happen once we bring in those privacy principles and start combining. Basically, data minimization and individual rights. So, we call this slide from the previous lecture. We said that ideally, we want to somehow get some DP guarantee even with respect to this. So by the time the server sees something, we want the server to already have some DP aggregate. And then as we walk away from the server and the surface of attack starts getting bigger, that DP guarantee gets stronger and stronger. So how can we do that? The question is how do you do that? With just DP alone, you cannot do it. You need to actually employ other techniques that we heard a lot about in the summer school. There's 3 classes of such techniques. So one thing to do is if you can rely on a trusted third party. So if there's a separate entity, let's say instead of Google, there's a third company or a second company, that we have more trust in, we can send our updates to that company, and that company could aggregate those updates, add the noise, strip off attributes, remove identifiers, or mix them together, shuffle them together, and forwards them to people. That already is a way of actually relaxing the trust that we put on Google. Now we need these two companies to come together, collude, in order for them to track who's sending what, and for them to remove that noise somehow. So this is essentially relaxing trust by having a trusted third party. Then there's a class of technologies that's growing in popularity, and we've heard about in the summer school, which is using trusted execution environments. So if we can have dedicated, isolated hardware in which anything we send into the hardware is encrypted, so we can't actually see things going through that hardware, and it's isolated from the rest of the system. And then inside this thing, we could aggregate those updates, we could add noise, we could have remote attestation, we could verify that we're indeed aggregating the number of updates that we claim to be aggregating, we're indeed adding the Gaussian noise that we claim to be adding, so on and so forth. This is a promising direction. There's obviously a lot of flaws in it. There's scalability issues. Now you have the root of trust as the manufacturer of this hardware. So there's lots and lots of caveats. I think Yuri also discussed some of them. So you need to be aware of the potentials, but also the drawbacks of this technology. And then, there's the old and tried cryptography and things like multi-party computation, which we heard a lot about, via either a single server, which I'm going to touch on, or multiple servers. And that's another way to ensure that the server will only get to see those noisy clipped updates rather than the raw updates or the unnoised updates. So let's dive into the third one, because that's the one that's most mature from our view. So single server secure aggregation is just an MPC protocol, it's a multi-party computation protocol, that allows a server to obtain the sum of these high-dimensional vectors, the model updates, without being able to inspect individual grades. And you saw lectures in this summer school on how to do secret sharing. There's obviously, in the context of ML, in the context of cross-device federated learning, lots of challenges, because these devices can drop out during the process itself. So if you start by sharing secrets across users, and somehow one of the users drops off, goes offline, and somebody is adding a secret share, it just makes the whole sum look like garbage, right? So we need a mechanism to remove those things and kind of control for dropouts. But you can also ask, what if a fraction of the clients collude together? Can they break the security of the protocol? So there's a lot of interesting challenges. And again, I'm not a cryptographer, so I'm not going to pretend to explain this protocol. The two papers from our team are actually listed on this slide. But if you understand secret sharing, and if you've attended the prior lectures, I think this would not be difficult for you. This would actually be easy, especially for the cryptography folks in this audience. So we're going to treat it as a closed box. For the sake of this lecture, we're not going to dive into the implementation of it. It's a multi-round protocol. In our use case, the users can't talk directly to one another. It's very hard to get phones and devices to communicate directly and share secrets. It's just not very possible at scale. So everything has to go through the server. So they have to share keys and exchange amongst each other some secrets through a server. So the trust model is slightly different what you see in the classical MPC literature, where these clients can talk directly to one another. So those are some of the caveats that I want to be very clear about. But if you assume an honest but curious server, you still get the protections that naturally secure aggregation people give in any one of the papers. So Yuri.
I just have a quick question. So why specifically MPC? Why not, for example, homomorphic edition? Why that's not just wondering for the secure aggregation?
This actually boils down a lot to homomorphic edition.
Yeah, this is why I'm just wondering. The secret sharing might not be necessary. Homomorphic edition. All right. So how do we leverage this?
The easiest way to leverage this type of a technology, if we have it, is to do the following. We can clip the gradients, the model updates that we compute on device. Now, obviously, we need to discretize. We need to go to something like finite group, because all these cryptographic protocols operate over finite groups, right? So I can't send floats. I can't just clip the gradient and send floating point numbers or reals. I have to convert those things to integers in a finite group. But let's say we have a way to do that operation. We understand it fairly well. And then I could execute the secure aggregation protocol. And now the server, what it sees is just the sum of the clipped model updates. So already that's a big improvement, because instead of seeing the individual clipped gradients from the clients, now it sees only one aggregate. It can only see the sum of the clipped model updates. So that's one big improvement. And now the server can actually execute this binary mechanism, the one that we discussed before. So that already reduces how much we place in terms of trust. And we've used this, and the paper that I'm referencing describes how we did it for one of the Gboard models, where we combined secure aggregation with the DP-FDRL protocol that I just presented. But you can go one step further. You can say, what if I don't want to trust the server in terms of adding the noise? So I don't want the server to do anything. I want the server to already see a differentially private output. So here what we're doing is we first discretize the updates. We clip and discretize those updates, or turn them into integers on a finite group. And then we add shares of integer noise on that finite group. And we then execute the secure aggregation code. So every device is going to add a little bit of noise. We're going to add all the noisy clipped discretized vectors together so that the server would see the yes.
How do you make sure that the server can only decrypt the final result?
Yeah, so this is, again, this goes back to the details of the cryptography that I actually lost over completely. But essentially the idea is very simply, if you and I can share some secret shares, so I'm going to add plus 1 million, and you're going to subtract minus 1 million to your value. And if I send my value to Google, say, and Google doesn't know that 1 million, it's a secret that we both know, but Google doesn't know it, right? So if I send my value to Google, with respect to Google, it looks like it's just a random value, because I added plus 1 million to my value, and you subtracted minus 1 million. But it's only when Google actually sums these two together that it gets the right sum, right? So now how do we do it through Google? That's the trick of essentially how do we share secrets. And it has to be done through some public-private key infrastructure.
But that would mean that the number of clients would need to be fixed a priori, right?
Yes, the report goal, the number of clients per round is fixed a priori.
And also the list of clients.
The list of clients doesn't need to be fixed. Yeah.
Still, I'm just wondering, why just not use FHE? This is like to simplify. Why use secret sharing in this case? Why? This is maybe my original question was like.
I mean, I guess let's talk about
add everything. I mean, everyone could add something to ciphertext, and then you can decrypt it. Just in terms of just.
Yeah, but I think at the basic property that we need, what is it then? We need secret shares of client-held values for that case, right?
No, I mean that's why I was saying, like, why use secret sharing at all? Why not just do FHE with like single key FHE? Just wondering, when we set up, why do we need to like actually use emphasis?
I don't think it's a must. I think there's probably variants that are probably more efficient that could just use FHE. I'm not the cryptographer, so yeah.
But if the server knows the key, then the server could already decrypt the inputs. So with FHE, you would need an interactive decryption procedure with more than one party.
Yeah, I guess what the requirement is. I mean, it depends on what's like. For instance, one fresh ciphertext to be shared with a certain key, and then everyone adds to that ciphertext, and then the server gets the result. I mean, just conceptual. I know it's, but it just seems like secret sharing is making it more complicated, unless it's needed for some other reason. Maybe secret sharing is needed for something else, and we use it.
Yeah, I mean, I can get back to you on this one.
Yeah, just was wondering, because it's a very simple complication.
Great. Okay, so yeah, for the sake of this lecture, I'm just treating this as a closed box. We can discuss offline the right primitive that we want to achieve. Cool. So this is the high-level idea of what we call distributed differential privacy, because now the DP is not executed by the server; it's not centrally applied. It's distributed across devices, and we don't really need to trust that the server is going to add the right noise, the right amount of noise, in the right place. Each user can actually do that. And the code that runs on the user, you can open source that, and people can actually do attestation on it locally on their device. So you can actually verify that indeed my device is flipping, is discretizing in the proper way, is adding the right type of noise, etc. So you don't need to do much beyond verifying those completely distributed components. All right, but here's the issue. There's a lot of challenges. You know, something I glossed over is like, what kind of noise do you want to add over this finite field? We can't just add Gaussian noise, right? Gaussian noise is continuous random variable, floats, real numbers. That's not something we have access to, especially if we're using low precision. We care about communication, and we want to reduce the number of bits we send back from the device to the server. We're operating, say, over 8-bit fields. What does it mean to talk about Gaussian noise over 8-bit fields? If it's 32 or 64, maybe you can approximate Gaussians pretty well. But over 8 bits or 16 bits or 12 bits, we can't talk about proper Gaussian noise. And so, like, how do we analyze the sum of these integer noise shares that we're going to add to get that proper DP guarantee? How do we do tight composition with that kind of noise? So there's so many challenges. It took us several years. And so I'm going to quickly overview how we did it and how we kind of think about it. So XI here represents the model update that's computed on the device. So remember, I had a slide where I said there's a client optimizer. So you run that client optimizer. And once optimization on device is done, you get a vector. That's the model update, all right? So that's a vector in RT representing the model output. And then you apply clipping. This is simply just L2 clipping. Again, it's an operation done in the real domain. And now what you do is there's a few operations that are critical. You need to do them to go from floats, from real vectors, and to integers. So the first thing we do is an operation that's called flattening. And what flattening is mathematically is just a random rotation. So what is a random rotation? We take a vector that has an L2 geometry. We know it has an L2 geometry because we did the L2 clipping. So we know it has bounded L2 norm because of the clipping, right? So we know it's on some sort of sphere in RT, L2 ball in RT, with a fixed radius. That's the L2 clip operation. So that's the L2 geometry of the vector. And we want to move from L2 geometry to L infinity geometry. So what is L infinity geometry? It's a vector where I can bound the range of every coordinate. That's the L infinity one, right? So how do we do that? This random rotation has a very nice property. If you studied statistics or probabilities, if you take a vector on a sphere, on or inside a sphere, and you apply a uniform random rotation to that vector, you can then bound with high probability the L infinity norm of that vector. So that's just for us to actually be able to bound the range of the entries of that vector. Because the next step, we're going to discretize. So how do we know how to set the range of this discretization? That's how we do it. L2 clipping plus this random rotation or flattening step will give us a proper range to use when we discretize. And so the discretization, what we're going to do is we're going to scale up. We usually scale in order to minimize the rounding error. So you take the values and multiply them by a very large number, depending on how much precision you have. That scale is dictated by how many bits essentially you can send. And you do randomized rounding to the nearest integer. Randomized rounding makes sure that you get an unbiased estimate of these values. So this green box, after this green box, we would have moved from RD to ZD, to integers. Still, we might have values that are very large, so we're not in a finite domain, but we are now at least on integers, all right, so ZD. And now we add integer noise. So now you can think of distributions over ZD, just like we can think of distributions over RD. Now we can think of distributions over ZD. I'll tell you about two of them. And now you could then do a modulo operation to bound the range of these integers, to go to a little finite group or a finite group. And you can then execute the secure aggregation program to see the sum. On the server, you just need to unscale, remove that scaling parameter, and you need to unflap it, just unrotate. That's it. And then you'll get a DP estimate of the sum. This is pretty technical, and I'm not diving into the little details of it, but hopefully the intuition, the high-level intuition of how we do it is not too hard. So what kinds of integer noise should we add? This is here, if we have cryptographers in the room, they should like this. Turns out we add discrete Gaussian noise. What is a discrete Gaussian noise? It's exactly what you kind of can think of. You take a continuous Gaussian PDF distribution, and you replace the continuous variable with a discrete variable. And now you're over integers, so you need to change the scaling of the distribution to make it sum to 1, to make it a PMF rather than a PDF. So it looks a lot like a Gaussian. I'm showing you some discrete Gaussians here with different variances, different parameters. And here's the funny thing. The funny thing is that that's something I didn't know. Apparently, cryptographers knew it a long time ago. When you take continuous Gaussians, independent continuous Gaussians, and you add them, we all know we get a Gaussian, right? Sums of independent Gaussians is a Gaussian. Turns out that when you take independent discrete Gaussians and you sum them, that's not a discrete Gaussian. It was a big surprise to me, at least, when I saw it. But you can just do the math of it. And it turns out that these things don't sum to a discrete Gaussian, but you can very nicely bound the distance between that distribution and the PDF of the discrete Gaussian. So a lot of the work we did in this case is to kind of control that distance very nicely. And it turns out that in lattice cryptography, there's a lot of work on essentially this problem that honestly I don't even understand myself. It's very advanced. The other distribution that I like even better is called the Scalon distribution. If you haven't seen it, it's just a fancy name of the person who actually came up with it. But in fact, it's just the difference of two Poisson random variables. Again, all these we can generalize them from scalars to multidimensionals, so IID over the D dimensions. But if you take the difference between two independent Poisson random variables, you get a pretty nice discrete approximation to the continuous Gaussian distribution. So this is called the Scalon distribution. And Scalon, unlike discrete Gaussian, it's closed under summation. So you take two Scalon random variables, you sum them, you get a Scalon. Simply because if you take two Poisson random variables and you sum them, you get a Poisson random variable. So they have very nice properties. And both these distributions behave a lot like Gaussian. So if we are operating over fine precisions, you look at their PMFs, they really approximate the continuous Gaussian variable. So a lot of the work that we put into this is in terms of analyzing their sums, proving tight DP guarantees on them, and doing tight composition across rounds for them. So that's where a lot of the work went. And I wanted to show you how they compare to centralized Gaussian. This plot is very packed, so let me just unpack it a little bit. You'll see three different kinds of noise distributions. There's at the bottom this Gaussian mechanism. This is the central floating point Gaussian mechanism. And then there's the discrete Gaussian. And then there's the Scalon with different number of bits I'm using for that precision. What you will see is that with just 12 bits, both the Scalon and the discrete Gaussian aren't able to give you the right privacy accuracy trade-offs. With that bit width, you're going to get poor privacy accuracy trade-offs. You can see how for small epsilons, the accuracy just diverges. It goes very low. But if we have 16 or more bits, we can actually match precisely the privacy accuracy trade-offs of the centralized floating point Gaussian. So with just 16 or 14 bits, we can do exactly the performance of floating point centralized Gaussian, but we can do it in a distributed way, also while reducing the precision down to 16 bits. So this is very nice, and we've actually used this in production as well. So we trained the smart text selection. That's the model that we talked about yesterday, where if you put your thumb on the phone, it automatically selects what it thinks you're trying to select. So an address or somebody's email and so on and so forth. We trained it with distributed DP, secure aggregation, DP applied on device, all the process. And we have a recent blog post that talks about this, this product launch. One thing though that I wanted to say here is that the epsilon we were able to achieve is not that great. It's in the double digits. It's not even in the single digits. So it's even weaker than what I showed you before. And the only reason why it's weak is because here we are simulating the DP feta. We're not doing this trick. We're not distributing these types of advanced stateful mechanisms. We're just doing DP feta. And we cannot use any amplification via sampling. Plus, the population is actually quite small. So we cannot use very large batches. The number of devices that run this thing is quite small. So this is where I want to briefly touch on this question of, is it okay to train with large-ish epsilon? This was the question that was asked, like, is it okay to achieve an epsilon of 5 or 8 or 10 or 12? These are large values. What does it even mean? So in theory, no, it's not okay. In theory, these epsilons don't mean much. If you just want to go with the worst case bound that DP gives us, epsilon of 5 already, if you look at this plot that shows how the belief of the adversary improves upon observing an epsilon DP output, you'll see that, if I start going into like epsilon of 3 or 4 or something like that, already the belief gets amplified a lot upon the release of something with epsilon equals 5. So really we need to be kind of as close as possible to this y equals x axis here. And that requires us to be in the epsilon less than 1 kind of regime. But this DP assumption makes it makes a lot of worst case assumptions. It assumes that first of all we have worst case neighboring data sets. That's something we spent a lot of time on in the prior lecture. It assumes an infinitely powerful adversary. By infinitely powerful, it's both statistically and computationally. So it can perform any complex attack or computation. It has infinite power, and it has access to infinite statistics. It knows the distributions and everything you're doing. And it also assumes that the adversary sees all the intermediate model updates. And there was a question in the previous lecture about, do we gain by hiding the intermediate model updates? And the answer was yes. But DP assumes you actually see all of those things. When we do composition across training grounds, we're actually assuming that the adversary can see the trace of all model updates. And even more importantly, there are operations that we simply don't know how to bound properly. Like, for instance, if I take the data set and I shuffle it, and then I go in disjoint batches, and I don't tell the adversary who appears in what batch, which user appears in what batch. Naturally, that should boost the privacy, right? That's introducing some randomness in the participation. We don't know how to compute tightly the epsilons under this model of accessing the data set. We shuffle the whole thing. In federated learning, we cannot uniformly sample the clients, but we know that the clients are only going to appear in 1 out of n training rounds. We don't have any belief to assume that the adversary will know which training round those users are participating. We just don't know how to mathematically model that and tightly bound the epsilons relative to that participation pattern. So there's a lot of things that we simply don't know how to tightly control. Either we're limited by the math or the model, And that's why if we just go with the epsilon and we say, okay, 5 is bad, 8 is bad, or 12 is bad, we would be shooting ourselves in the foot. Because that 5 or 12 is computed under a lot of very worst case assumptions, as you can see. In reality, the actual leakage can be a lot better. And that's why, we need to think about a complementary technology that we can use in addition to DP, which is attacks. Can we attack these models that we've trained with DP, maybe with an epsilon that's in the high single digits or even in the double digits, and can we see what happens upon these attacks? So this model that I told you about, the smart text selection model, we used a method to attack it. It's called the secret share method, and maybe it was discussed in this summer school. So the idea is that during training, you insert some out-of-distribution training examples. These are called canaries. So you should think of them either as watermarked images with random labels, or some nonsense phrases that we've constructed. These are secrets that we plant in the training process. We have a way in federated learning to create these synthetic users with these secrets and let them participate in training under the protocol that we've used. And then we train the model. We use exactly the training methodology, the distributed DP, that same training methodology that we just discussed. And then after we train and we obtain the model, we take the trained model and we try to test whether and to what extent the model has memorized these canaries. Can we extract those canaries from the model? Has it overfitted to those canaries? Has it memorized them? Can I put in some inputs and make it generate those outputs or something that tells me that it has seen those secrets? And so to the extent that we can extract those canaries or secrets tells us something about the privacy guarantee of the model. So typically the way we do it is we try to measure the rank of, the output of, that canary that we see. So over all the possible outputs, let's say it's a language model, and it could output, a bazillion token, depending on the vocab that you're using, the tokenizer that you're using. If you have a certain sequence of tokens describing that secret that you added, that canary that you added, you try to see how often does that sequence appear at the output of the model when I poke it. So that's called the rank of the canary, or the rank of the secret. And so we did those studies, and we did them for the smart text selection. And what we've noticed is that even if you add very little, so simple add here is train without DP whatsoever, no DP, just clipping a thing. And the second column shows if you add very little noise, 0.01, that's a triple digit epsilon, not even something that you would care about. And 0.1 is a double digit epsilon, that's very weak DP. And even with those low standard deviations, low noise, we were able to improve the privacy of the model by a lot. So we went from a rank that's possibly very low. If you see those natural language canaries or secrets, they have very low ranks, meaning that you could extract them easily from the model. We go from that to something very close to 50%, which is kind of a random guess at the output of the model. And so this suggests that even with very little noise, under realistic attacks, you get substantial improvement for training with weak DP. And by the way, these attacks were done at the user level, so there's a lot of very nice properties to them. All right, so these are called reconstruction attacks, what we just described. But we wanted something that's more grounded in the language of DP, and those are called membership inference attacks. And Jan talked a lot about them. You've seen them, and I think some of you have even worked on these attacks. What are membership inference attacks? Reconstruction attacks, we're trying to reconstruct a training example, either partially or fully. Under membership inference attack, we're actually asking a much simpler question. We're asking, if you give me a training example, can I guess whether or not it was used during training? So if you give me a model and you ask the question, was Peter's data used during training, yes or no? So it's a very simple binary question. You can see how these attacks are easier to conduct. And it turns out that these attacks are actually very closely related to DP, because DP can actually be viewed as a membership inference attack. So there's this operational interpretation of DP that maybe many of you have seen, where the way we kind of explain DP operationally is as follows. So you're going to take either D0 or D1. The difference between these two data sets is, again, a single record. That could be a user or a single training example, depending on the unit of privacy. You're going to pick one of them at random, flip a coin, and pick one of them, and then train the model on the data set that you picked, either D0 or D1. And then you're going to output the trained model. You're going to give it to some adversary or auditor. So the auditor does not know which one you picked. It does not get to see whether you picked D0 or D1, but it sees the output of the computation. And it tries to guess, based on this output computation, did you pick D0 or D1? Again, it's a very simple binary hypothesis, that sort of binary question that you ask. And it comes up with some sort of a decision. The parameters fall in this region R. I'm going to assume that you've trained it on D0. Otherwise, if it's not an R, I'm going to assume D0. And if it is an R, I'm going to assume it's D. That's called a decision rule. So if you sweep over all possible regions in the output space, you are sweeping over all possible decision rules. Simply by traversing all these sets R, you're sweeping and traversing all the possible decision rules that any adversary can make. And what DP tells us, and this is very exciting, is that if you train with DP, that algorithm that we use is provably epsilon delta differentially private, then it bounds the performance that any attacker can get. So no matter how complicated your attacker is, no matter how computationally intensive it is, and no matter how good it is, statistically and or computationally, if you perform these tests, there is a bound on how high the true positive rate can be of this attack subject to some condition on the false positive rate. So that's the beauty, that's the connection between DP and membership. These two are exactly equivalent. There's a one-to-one equivalence between them. And this is something I actually worked on in my own PhD, but then there's a long line of research papers that have developed this idea and did membership inference attacks based on it. So this is basically what I want you to think about as we close this talk. There's no one single threat model. There's actually many different threat models. And we can think about, what does the adversary care about? These are the goals of the adversary. Is it trying to answer these binary questions? That's more aligned with DP, and those are membership inference type questions. Or is it trying to reconstruct training examples? In the case of generative models, especially language models, usually this reconstruction is something that is more operational. We're afraid that if Google trains an LLM, and if somehow that LLM uses my emails, I don't want somebody else interacting with the LLM to somehow suddenly see my own email, my personal, email or something that I discussed with my colleague or with a sibling or something like that. So these reconstruction attacks or memorization attacks tend to be more, from an engineering standpoint, operational in the context of generative AI models. But membership inference ones have stronger ties with DP, so they are more grounded in the semantics of the French. And then, we should think about the adversary's knowledge. Does it have open box or closed box access? Usually these are known as like white box versus black box. So can it see the parameters of the model, or can it just have an API access and only sees the output of the model? Can it see the intermediate checkpoints, the model iterates, or can it only see the final model? Can it have partial or full knowledge about the training set? Maybe the adversary knows something about who participated in training already, and that can help it. So we need to kind of, be explicit about the adversary's knowledge. And then the adversary's capabilities are just as important. So can we audit by influencing the training data? Can we inject those canaries that we talked about, those training secret examples? Can we audit by influencing the training process itself? Can we inject gradients that are fake into the training, so bypassing the training data and going into the training loop itself? That's an even stronger attack in some sense. And can we only audit at inference time? So I cannot touch the data sets. I cannot touch the training loop. I get something and I need to live with it. And I need to try to do these attacks and auditing at inference time. So you can pick, where you want to be on this spectrum. For instance, you can say if we are in the red category, if we want to do membership inference, and it's open box, I can see all the parameters, and I can only see the final model, and I can influence the training process. That's one, let's say, instance of a threat model, very grounded and very precise. Or you could say, no, actually, I care about the blue category, which is I just want to do reconstruction attacks in a closed box sense. I cannot see the parameters of the model. And I only have, let's say, partial knowledge of the training set. I cannot tamper with anything other than the training data. I can put in some maybe canaries. And that's the secret share method that we talked about. But you can have different, you can slice and dice this differently, and you get different interesting threat models. And so I will close on this note, but I wanted to say something here is that we are by no way near having a comprehensive analysis for how strong all different combinations of attacks are. And so there's gaps between DP and instantiations of these attacks. So another very open problem that you folks can participate in is strengthening these attacks and exploring different combinations and tying them back to DP, understanding when the guarantee of DP is tight. It is what it is. It tells you exactly what happens, and you can match it via an instance of an attack. And when it's actually weak, in reality, if you do attacks, you're getting much better leakages compared to what it predicts. So having this comprehensive view is still lacking in the community. So that's what I think we should do. So I'll stop here and thanks a lot.
Thank you, Peter. Are there any questions? Yes, there's a question.
So this is my use. Usually, level DP is necessary to unlearning someone as well, like seems to guarantee that, right?
Yeah, that's a very good question. So the objective of machine unlearning and DP, these two objectives are actually very different, but DP is stronger than machine. The DP implies unlearning, but if you only care about unlearning, you don't have to pay a device. You can get it essentially at a smaller price. So machine unlearning is something we didn't discuss a lot. I briefly mentioned it in the first lecture. What it is say I've trained a model on a data set, and now suddenly somebody comes to me and says, hey, I want you to forget my group. You could, obviously, the very basic thing to do is to say, all right, I'm going to take that data set, I'll delete Peter's training data, so you get a new training set without Peter, and you retrain a model completely from scratch on that small data set. So that's the perfect unlearning algorithm, right? But that's very inefficient, especially let's say somebody trained one of these huge LLMs, 500 billion parameter models. Retraining that thing from scratch is very costly. These things cost $50 million, maybe now these days $100 million. So you don't want to retrain it from scratch. You want to apply some fine-tuning type algorithm to erase Peter's data. And that's the area of machine unlearning. And so if you had trained the original model with DP, with good epsilon and delta, you could say, hey, look, already the model does not overfit to the data. I have this DP problem. That's technically already not overfitted to you. I don't need to do anything. But that's a strong thing.
Any more questions?
How do you motivate?
Wait for the mic.
How do you motivate product manager or engineers to actually use DP? What's the incentive you actually offer them, or what's the usual conversation you have?
Yeah, that's a very good question. In my career at Google, initially it was a bit of an uphill battle. You go to customer teams, tell them now you need to train with noise. Teams no data scientist and no engineer likes noise, right? They actually want better models and better signal, more accurate answers to tell them that you're going to get less accurate answers. So two things we did. The first thing we did is we said, hey, look, let's start with just training with clipping, no noise. And usually if you set the clipping norm properly, you're not going to lose any accuracy. In fact, in practice, we observe that you get good generalization, good robustness from the clipping. Once you're there, you're telling them, hey, look, if you actually had a teeny tiny bit of noise, you get a finite. You want to give it a shot? Why not? You know? And as you get into the finite epsilon, you walk your way. I mean, that's exactly what happened with deep words. You see, the first one was 8.9, and then we worked our way down to small epsilons. That's one line of attack. The other line of attack is the regulation. Do you want to be GDPR compliant with such and such? Do you want to be reactive versus proactive? Do you want to wait until the problem happens when you're going to fix, or do you want to be ahead of the curve? And in this case, honestly, competition is very helpful. If company X does something, it encourages company Y to do it. If there's a startup that's actually pushing the boundary of what can be done with privacy, it encourages the other companies, whether big tech or medium tech or small tech, to do it.
Yeah, I guess it's a common problem with all security vendors have that, security usually comes with the price in terms of efficiency or financial costs. Yeah. Are there any more questions?
From a legal perspective, for example, the right to be forgotten from GDPR, does DP satisfy those requirements? I mean, those hypothetical situation that you mentioned, would it be actually okay not to remove the data because you can guarantee that it's already private?
Yeah, so that's a great question. I'm not a lawyer. I can give you my own opinion, but that may not be actually the true answer to your question. We need to talk to regulators and lawyers. My understanding is that DP satisfies it, but DP may be a strong overkill. And for these things, usually, the right to be forgotten and copyright laws and things like that, they're in a very gray area in the law where usually it's on a case by case. So it's basically a regulation via case law is what they call it. And usually the courts, they appreciate if the company or the engineers have really put an effort. If they can demonstrate that they thought about this, they're not retroactively trying to fix a problem. They kind of anticipated and they show a log of things they tried. It may not be DP, it may be something else, a mechanism that they put in place to kind of do it, and they take that into account, is my understanding. So yes, so it's pretty complicated. There's no clear answer. If you talk to lawyers, they're also kind of not completely on the same page. At the end of the day, something is going to go to court, and it's going to be like a case law.
This is in the US, right? Because the US it has this law precedent. Probably it also depends on the legal system.
But I think even in GDPR, the right to be forgotten, there's been some challenges to it, and it's a little unclear. I mean, I've read a lot of articles where, what is this right to be forgotten? Is it machine learning? Is it DP? Is it something else? Do we enforce it through technical, like algorithmic? It's, I think, a little fuzzy. It's my understanding.
What to do with already trained model that costs millions?
Right. Yeah, I don't even understand what is a digital signature. Lawyers. That's about complicated.